Action and reaction are at the core of every spectacle known to the human race. Space exploration is one of humanity's utmost sumptuous and monumental endeavors, not only in the field of science, but overall in the impact that it has had on the world. Propellant transportation has enabled us to go up close to explore celestial bodies, but this is extremely hard as there are a plethora of factors involved: spatial vacuums, orbital mechanics, the logistics of the onboard systems, but the one carrying the most imperativeness is the thrust taken to lift and make the rocket attain escape velocity, a partiality without which we wouldn't have been able to be in the realm of spatial exploration we are in today. The rocket engine. So let's analyze the problem that this unit is trying to solve. There are many issues at play here, the main of which is to propel the rocket with sufficient energy so that it reaches escape velocity and goes into orbit, and then escapes that orbicular ellipse to angularly propel at the relative destination. It is acutely easy as spatial vacuum makes sure that there is no force to slow you down, though the preeminent problem is faced when generating that modular thrust, which is where the theoretical and current practical solutions come in hand. Rocket engines use rocket propellants as reaction mass to expel high-speed propulsive jet fluid as to eject themselves from the surface. You may have heard of Newton's third law. Every action has an equal and opposite reaction, same in magnitude but different in direction. When the exhaust is thrown in one direction, the rocket benefits from the other direction and takes off, in the same way that a repulsion is produced if you shoot a shotgun. The aftershock reaction causes you to move backwards. The same principle is used in rockets. At this point of time, there are only two main types of rocket engines, those being chemical rockets, or ones that work by exothermic reduction oxidation systems, and thermal rockets that work by electrothermal propulsions, which means that they use electricity to create thermal energy and heat and release this to lift the rocket. Since the main source of energy in the thermal and chemical rockets is hydrogen, this means that the fuel is extremely light, making it more effective. The many parts of a rocket work in unison to create the thrust that is needed to lift such a complex machine off the ground. For example, the oxidizing reagent oxidizes the fuel and then passes it to the combustion chamber, where the fuel is combusted and is passed through the exhaust, which dictates the amount of thrust produced. To calculate the net thrust, an equation can be used, that being that net thrust is equal to exhaust gas mass flow times the effective exhaust velocity, which is equal to gas mass flow times effective jet velocity plus flow area at the nozzle into static pressure at the nozzle minus atmospheric pressure. This can give us an approximation of the net thrust which is used to lift a rocket, though not everything is positive about this invention, which brings us to temperatures of above 3500 degrees Kelvin inside the core can cause specific materials to lose their strength, and that is where the first major issue is introduced: cooling. Rocket engines have gas turbines in the hot exhaust. Due to their large surface area, they are harder to cool, and hence there's a need to run the combustion processes at a much lower temperature, which loses efficiency. To solve this dilemma, some rockets use ablative walls, which are walls that are lined with a material that is continuously vaporized, and hence the material in contact is also carried away, which cools down the engine. Another technique used is regenerative cooling, which introduces cooling jackets inside of the oxidizer and the injector of the rocket, which cools it further. Another problem faced is the lack of thrust these rockets can produce. The fastest rocket to date, according to NASA, is New Horizons, which can reach a maximum velocity of 50,000 kilometers an hour. Though this is not ideal for deep space travel, as it can only cover a mere 7 light hours in 10 years, and that is where you come in. Funding is immensely needed to continue spatial operations. Companies like NASA are only getting a fraction of the federal budget, and this number is reducing by the year. More funding is needed to look into theoretical designs for a faster and more stable rocket engine. There have been many concepts for fusion rockets, ones which use nuclear fusion as a power source for the propulsion, which can increase the potential of the thrust generated by these rockets. If we can put designs like Project Daedalus and Orion into practical views, then we can be the ambassadors of change. And not only will this benefit us as humans, but it will also benefit the economy. By investing in such a project, a large spectrum of possibilities can be unlocked. Deep space travel could mean opening up a new business sector in the realm of interplanetary transportation. The lack of resources causes the price to go up for raw materials in the world we live in today. But if we get access to other celestial bodies, we can get their natural resources. And since there will be a higher supply, the price for raw materials will go down, liquidating the market, increasing opportunities for customers, and increasing the surplus of companies willing to invest in this new sector. The simple action of investing in this plan will have a large impact on the community. We are the environment around us, and by investing in this environment, we are investing in our future and into the start of a new space age, one that we can be the pioneers of by using a simple tool and innovating on that to benefit the whole human race. Action and reaction.